In our previous session, we made a big improvement over the rectangular rule by replacing rectangles by trapezoids. The reason that worked well from a geometric point of view is that the trapezoids fit the function much more accurately than did rectangles. So we found that this trapezoid rule decreased by an entire order of magnitude or more the error that would be given from rectangles of the same width. One downside was that we had to evaluate both the left and the right side of the trapezoid, at first making us think we had to double the number of calculations. But that didn't even turn out to be a problem because we could note that the right side of one trapezoid had a height that was the same as the left side of the next trapezoid. So we really just needed to take the interior points and calculate them once, multiply by 2, and then make sure that the far end of the left and the right points were only evaluated once. There was really no difference in the computational cost using a trapezoidal rule compared to the rectangular rule. Can we do better yet? Well, obviously the answer is yes, or we wouldn't be marching on to section 5.1b. So here's a summation. This is really what we did last time, where we had a grid structure from x0 to xn. So there's n plus 1 total points, or n intervals of interest. And we handled the extreme ends, the extreme left and the extreme right, separately, adding those two function evaluations together, multiplying by the width of one trapezoid and dividing by 2. That term, if we separate it out, could then be added to simply the sum of all function values times h. Why isn't it h over 2? Well, because we have two uses of each functional valuation times h over 2. So those two cancel out, and we have a very efficient formula. Let's see if we can't even do better than that by arranging the sequence on how we do the trapezoids. We're going to need to generalize this term s sub t to allow for a certain degree of recursion. There we're back to that word recursion again that we've talked about occasionally off and on in the whole course. And we're going to use it again here. What we'd like to do is, using our basic multi-trapezoid rule, in other words, the trapezoid rule for many trapezoids, and cut each of the intervals in half. So I'd like to say, if I had a certain degree of error on this formula, how much better could I do if I used h over 2 as my width? Now, if I do that, a consequence will be I'll have is twice as many intervals. So I'll need to sum up from 1 to 2n minus 1, where this n and this n are the same thing, and still have two endpoints. The endpoints will now be from 0 to 2n. But don't let this 2n fool you. X sub 2n is the same right value that x sub n was here. So our doubling of intervals, which requires a reindexing of all the points, are still covering the same width of the interval that we had to begin with, just twice as many intervals to work with. Well, we use the same formula. And to accomplish the new portion of the formula, we have many more interior points. We're going from 1 to 2 sub n minus 1, and we multiply by a half-sized interval, but we still evaluate the function at every location across this new grid structure. Well, let's take a closer look at whether we have or haven't reproduced calculations that we already did up here. Since we cut the intervals exactly in half, that means every other point that we're calculating in the second equation was done in the first equation. In fact, every point in the first equation is represented in the second equation. There's just the odd ones that are missing. x0 is still x0. What is now x2 used to be x1. What is now x4 in this sum used to be x2, and so forth all the way through the summation. So we have calculated half of the values already. If we could figure out a way to separate out those we've calculated from those that we haven't, we could just reuse the formula we had on the previous iteration and only calculate the new values. That turns out not to be very difficult. So let's give it a try. I need to improve my notation a bit though. So I am going to call this sum of trapezoids. I'm going to include now a superscript that represents a recursion level or a doubling level. So and this recursion number or sequence number can be used to track the width as well as the total number of intervals n, because the number of intervals are simply going to double each time. Therefore, n will be just 2 to the m when we develop the algorithm. Well, let's take it a little bit further and take a look at one big large interval. So we're integrating from a to b, and I'll redundantly call a x0 and I'll call b x1. And I'd like to do a trapezoid rule across the entire interval. Well, I know how to do that. I just take the two endpoints and we average them and multiply by the width, which I'm now calling h sub 0. That's just the ordinary trapezoidal rule for 2 points. Now I would like to cut this interval in half. So let's just go ahead and do that. We're going to have a h1, which will be half the width of h0, and we'll use it twice to cover the same span. We'll renumber each of the grid locations, starting with x0, the same place x0 was before, but we have a new middle value called x1. We never calculated that before, and a new x2 that is coincident with the old x1. Well, we can go ahead and use the trapezoidal rule for 3 points by simply taking the average of the endpoints and multiplying by the new width and adding in all the interior points. Well, the interior points this time consist of just one, and that is x1. Notice how we have already calculated this portion of the formula before. This used to be called x1, but it is the same location as what is x2. So it seems to me that if I preserved what I had calculated previously and simply added h1 times f of x1, I would have the trapezoidal rule that had half the size intervals. Well, I bet I could do that again. If we set m equal to 2 and cut each of the h1s in half, then I would end up with 4 intervals of half size each. So we'll call them h2, and there will be 4 of them. I'll end up having twice as many intervals as I had before, 5 points now instead of 3, and 3 of those points were calculated previously. So could we take advantage of that? Well, the formula now becomes the two extreme points, f of x0 plus f of x4, again multiplied by h2 over 2, and we have to add all the interior points, x1, x2, and x3. Now x2 I did before. That was part of my previous formula. So only 2 of them have yet to be calculated. I bet we can do this again. If we cut the interval in half again, we're at recursion level 3. Again, we've cut the intervals in half, use the same formula as always, and add up all the interior points times the new interval. Well, all of the even numbered interior points were calculated before. The x1 is new, but x2 used to be called x1, x4 used to be called x2, x6 used to be called x3. So if we take those even numbered functional evaluations and move them off to the left, we should be able to pick that up from the previous recursion level. And let's just do it one more time. We continue to cut in half, and we're going to separate those values that have already been calculated and try to use them again. Now we need to develop that, but that's going to be the nature of how we're going to do this. The big advantage you should be able to see at this point is the error estimate should be able to be calculated at each recursion level. And so you can calculate the error and stop when the error gets small enough. But since we're never repeating calculating any functional evaluation, we're not going to do any more work than we did when we did the sequential method in the previous section. It's going to be the same work. We're just doing things in a careful order, cutting the intervals in half and giving us the ability to stop the algorithm when we need to. So let's just review again what these terms are. The total number of subintervals will be 2 raised to the recursion number. Go ahead and verify that. The endpoints will always be called x0 and the largest n, x sub n. So that corresponds to our a and b values. The width of the interval will always be equal to 1/2 to the mth power, the recursion level, times the original interval that we're trying to integrate over. And we can rename the grid points. We could rename the grid points as being the starting point plus a multiple times whatever the interval width is at that time. Okay, so with that notation in mind, let's redevelop our trapezoidal rule, taking advantage of all previous calculations, but doing it in this recursive manner. This becomes the general formula using this notation of recursion level m using the normal trapezoid rule. So the first iteration, not the zeroth iteration is one that covers the whole interval at once. This is the one that has 2 endpoints combined together and only one interior point. We could rewrite that in terms of the original h0, the whole span, b minus a, and replace f of x0 with f of a and f of x2 with f of b. If you look carefully at the left portion of this formula, that is the 0th order recursion level. And this is the interior point that had not been calculated. So we could just go back and call it s sub t of 0, where s sub t of 0 was the original full span trapezoid rule. And we just add the new width times f of the midpoint. Let's try moving to m equals 2. So the formula represents, again, the extreme points average times the relevant interval plus the current interval size times the sum of all the interior points. So we have x1, x2, and x3. We would like to pull out f of x2 because that had already been calculated, and we'll just leave in the odd values and combine this term with the previous term. Okay, by combining this all together, this is my s sub t of 1. This expression that I've pulled out only consists of previously calculated points. And with a little bit of algebra, I can factor out a 1/2 of all these expressions, and I end up getting exactly the formula I had for s sub t of 1. If I replace this expression with the s t of 1, with a 1/2 sitting out in front, then all I've got to add up is the odd interior points and multiply by h2. We can just continue this as long as we like, always preserving the information we have gathered before and moving the recursion level up by 1 more. Let's give that a try. So if we want to do this in general, and we want the mth recursion level, this being the actual formula, we can pull out all of the even index points and separate them from the odd points. If we do a little bit of algebra to that, we can replace the h sub m with the previous h, so m minus 1, but in order to make that work, we've got to cut it in half again. So h sub m is equal to 1/2 h sub m minus 1 by how we constructed it, and therefore we have a 1/4 out here. We'll make the same substitution here. hm becomes 1/2 h sub m minus 1. And now we'll pull the 1/2 out of this expression. And here we end up getting the exact same formula for the trapezoid rule for the previous recursion level. On this side, we just have the functional evaluation at each of the odd grid points multiplied by the new width. And when all said and done, we can write it recursively as 1/2 the previous sum plus the sum of the new odd interior points times the current width. And this is our recursive formula, starting with the s sub 0 and just moving it up to the next term.